Water, a precious natural resource. Without clean water, society as we know it would not exist. The demand for clean water is ever increasing, making the management of this limited water resource a priority. When water is consumed for use in our daily lives, it is also used as a vehicle to carry unwanted waste materials away from our homes and businesses. Treating this waste material in the water is the job of the wastewater treatment plant operator. The types and amounts of pollutants that must be removed vary across the state based upon the attributes of the receiving stream or watershed. Your facility NPDES permits spell out in detail what pollutants must be removed and what conditions must be met in order to comply with the permit in a lawful manner. Limits contained in the permit may fluctuate based upon the season. All treatment plant operators must become familiar with their facility NPDES permit and associated regulations. It is the job of the treatment plant operator to notify the system owner of any current or potential system problems that are or may cause non-compliance with any laws, regulations, or permit conditions. This video production is the first in a series that focuses on nitrogen in wastewater. This production will focus specifically on ammonia nitrogen removal. In your NPDES permit, ammonia nitrogen is often abbreviated as NH3-N. Typically, treatment plants that have permit limits for ammonia nitrogen have a tougher job when compared to facilities that have no such limits. In some cases, treatment systems may also have nutrient limits, such as total nitrogen or phosphorus, that require even more complex treatment. Now let's take a closer look at ammonia. Ammonia is a form of unoxidized nitrogen. Ammonia can be problematic if discharged into a receiving stream. If discharged, the ammonia can create a dissolved oxygen sag in the waterway, create acute and chronic toxic conditions for fish and other aquatic life, present problems for downstream drinking water supplies, create nutrient loadings when oxidized. Ammonia can be toxic in relatively small quantities. At concentrations as low as 0.06 milligrams per liter, fish can suffer gill damage. At a concentration of 0.1 milligrams per liter, water is typically considered polluted. At a concentration of 0.2 milligrams per liter, sensitive fish, such as trout, begin to die. At a concentration of 2.0 milligrams per liter, tolerant fish, such as carp, begin to die. The toxicity of ammonia is impacted by the water temperature and pH. Typically, the higher the temperature or pH, the higher the toxicity. Ammonia in wastewater can come from a variety of sources and is found in domestic wastewater. Non-domestic wastewater, such as industrial or institutional wastewater, trucked-in waste, such as septage, and internal recycle flows, such as belt press filtrate or anaerobic digester supernatant. It is important for the facility operator to document the amount of ammonia generated from all sources. For systems that have anaerobic digestion or that produce filtrate from belt presses, thickeners, or other devices, it should be noted that these process flows can produce a large quantity of ammonia. This is especially true during periods of malfunction. This makes monitoring and adjustment of these processes a critical factor in maintaining compliance. Always remember that solids handling processes and processes upstream of biological treatment processes can dramatically impact loadings and efficiency. It is easy to see why we would want to remove ammonia from wastewater. So how is this accomplished? There are a number of methods that can be used to remove ammonia. However, the most common and cost-effective for wastewater treatment plants is biological treatment in a process known as nitrification. Nitrification is a multi-step process utilizing autotrophic bacteria of the genera Nitrosomonas and Nitrobacter to convert the ammonia in the wastewater to nitrate. When ammonia is converted into nitrate, the nitrate is non-toxic. However, nitrate can serve as a nutrient in water. In many cases, especially in the Chesapeake Bay watershed, nitrate must also be removed from the wastewater as well through a process known as denitrification. Not all treatment systems are the same when it comes to nitrification. Some processes definitely work better than others. Typically, unmodified lagoon systems struggle with meeting ammonia limits and are the least capable when it comes to nitrification. While nitrification can take place in a lagoon, much of the gains made are given back as organisms die off and decompose in the bottom of the lagoon. Fixed film processes, such as RBCs or trickling filters, are capable of achieving nitrification under the right conditions. In the case of trickling filters, you may see a two-stage process. In the first stage, known as the roughing filter, CBOD is removed while nitrification is achieved in the second stage filter. Standard rate trickling filters would have the most difficulty in achieving nitrification, especially when compared to high rate or super high rate trickling filters. While fixed film systems can achieve nitrification, they would struggle with achieving denitrification without significant modification. In the activated sludge process, the extended aeration configuration works well in achieving nitrification and can be typically easily retrofitted to achieve denitrification as well. The long MCRTs provided in the extended aeration process works well for growing nitrifying organisms. The least capable in terms of activated sludge for achieving nitrification would be the contact stabilization process. However, many contact stabilization facilities do indeed nitrify. Regardless of the process, there are a number of factors that impact nitrification. These factors include efficiency of upstream treatment units and processes, dissolved oxygen, temperature, mean cell residence time, alkalinity, pH, CBOD removal, toxic compounds, wet weather operations, and facility design. Let's take a closer look at each of these factors. Factor number 1, efficiency of upstream treatment units and processes. From the time the wastewater is generated through the collection system and through all of the treatment processes in a treatment plant, the process of nitrification can be impacted by anything that happens upstream. For example, certain substances that could be accidentally or intentionally dumped into your system could cause the loss of nitrification. The development and enforcement of sewer use ordinances can reduce the likelihood of unwanted substances entering your system. After the wastewater is generated, it then goes into the collection system for conveyance to the treatment plant. In the collection system, if excess water enters the system, it can cause a washout of biological processes in the treatment plant. After the wastewater arrives at the treatment plant, the operator must monitor all treatment processes. Malfunctions in preliminary, primary, or solids handling processes can adversely impact the nitrification process. If your facility accepts or is considering accepting trucked-in wastes, be sure to review this with your engineering staff to assure your facility has adequate capacity to accept this type of waste. To maintain nitrification, the treatment system operator must be vigilant and take actions to prevent or stop malfunctions and undesirable events throughout the entire treatment system. Factor number 2, dissolved oxygen. Nitrification is a purely aerobic process that requires a large amount of oxygen. In fact, it requires 4.6 pounds of oxygen to oxidize 1 pound of ammonia into nitrate. Comparatively, it takes approximately 1.1 pounds of oxygen to oxidize a pound of BOD. The requirement to nitrify can almost double your oxygen requirements and aeration costs. As you can see from this chart, the specific growth rate of nitrifying organisms drops off dramatically at dissolved oxygen levels below 2 milligrams per liter. It is good if the dissolved oxygen level can be maintained near 4.0 milligrams per liter. If you find your dissolved oxygen dropping below 2.0 milligrams per liter, you may need to add supplemental aeration or increase the MCRT. In terms of oxygen transfer, fine bubble diffusion systems work better than coarse bubbled systems. This is important for maintaining the biological process and controlling costs. For fixed film systems, it is important to have adequate ventilation to maintain an aerobic environment. It should also be noted that in facilities that have an upfront anoxic zone for denitrification, there is a beneficial return of oxygen through the uptake of nitrate. This beneficial return can be up to 60% of the oxygen required for nitrification. Factor number 3, temperature. As temperatures increase, so does the activity of nitrifying organisms. As you can see, when the water temperature drops below 5 degrees C, little or no nitrification may take place. For this reason, permit limits are typically seasonally adjusted for ammonia removal. The specific growth rate of nitrifying organisms is tied directly to temperature. If nitrification is lost during the winter months for any reason, it may be difficult to re-establish nitrification. Factor number 4, mean cell residence time. The actual required MCRT for nitrification depends upon the previous two factors, temperature and dissolved oxygen. During colder months, the MCRTs will need to be increased to achieve nitrification, while the increased activity during the summer months will allow for a lower MCRT. If the DO drops, the MCRTs will have to be increased to compensate as well. The following chart can be used as a rule of thumb. However, the actual MCRT should be calculated. For every 10 degrees C rise in temperature, the rate of nitrification doubles, and the MCRT can be reduced in a corresponding fashion. Keeping good records is important. Charting the results of process control work can be very useful. In terms of fixed film facilities, the main process control is the recirculation rate. Increasing the recirculation rate would equate to increasing the MCRT. Factor number 5, alkalinity. The process of nitrification consumes alkalinity. In theory, approximately 7.2 pounds of alkalinity is consumed for every pound of ammonia that is converted to nitrate. Insufficient alkalinity will bring a halt to the nitrification process. If the alkalinity is not present in sufficient quantity, you may need to add supplemental alkalinity in order to nitrify. It should be noted that for facilities that have an upfront anoxic zone for denitrification, approximately 1/2 of the alkalinity that is consumed for nitrification is returned to the system through denitrification. As a rule of thumb, the alkalinity should not drop below 50 milligrams per liter at any point in the process. Factor number 6, pH. The broad range for nitrification is from 6.5 to 8.0. However, nitrification typically works best when the pH is above 7.0. pH readings outside the recommended range could lead to an inhibition of the nitrification process. A sudden and drastic drop in pH could indicate that all the alkalinity has been used up. Factor number 7, CBOD removal. In order for nitrification to take place, CBOD must be significantly reduced. If we do not have adequate reduction in CBOD, nitrification will not take place. CBOD should be reduced to below 25 milligrams per liter in order to facilitate nitrification. The efficiency of upstream treatment units is critical and must be monitored. In the case of multi-staged biological processes, CBOD should be reduced prior to nitrification. Typically, facilities that have upfront anoxic zone experience a significant reduction in CBOD through the anoxic process. Factor number 8, toxicity. Nitrifying organisms are more sensitive to toxic materials when compared to other organisms in the treatment process. Nitrification can be interrupted by the presence of toxic compounds. Effective pre-treatment and sewer use ordinances are a must. Be sure to have good communications with your non-domestic users in the event of a spill that may enter your system. In some cases, strong oxidizers such as chlorine or potassium permanganate can be used to pre-treat waste to reduce the toxicity of some compounds. However, care must be taken not to overdose. Factor number 9, wet weather operations. Many treatment plants in the northeastern United States experience problems with inflow and infiltration into their systems. This extra water enters the systems during wet weather events or snow melt-offs, oftentimes inundating the treatment plant with unwanted water. This often results in the lowering of the temperature and a washout of biological solids from the treatment system. A heavy washout of solids can easily lead to a loss of nitrification. All treatment systems that are impacted by inflow and infiltration need to develop a wet weather operations strategy. In short, this strategy maximizes the flow through the treatment plant while minimizing the washout of solids. Ongoing repair and maintenance of the wastewater collection system is essential as well. Factor number 10, facility design. As previously illustrated, the ability of a system to nitrify may be limited by design. Be sure to review your system design with your engineers if you have questions about design capacity. It may be necessary to add tanks, or in the case of some activated sludge systems, add fixed film media to the aeration tanks to increase the capacity to nitrify. In any event, carefully review your options with your engineers before making any significant investment. Remember, design changes at a treatment plant require prior approval by DEP. As you can see, maintaining nitrification through a treatment process requires close observation and action on the part of the treatment plant operator. From the point where the wastes are generated, through the collection system and through the entire wastewater treatment plant, the efficiency of all processes must be monitored and maintained. Regular microscopic examination of biological organisms can yield a wealth of information on the health and predominance of organisms in your treatment system. It is a good idea to graph the results of your process control tests and calculations. In any event, good record keeping and an effective process control plan are essential elements for proper operation and maintenance. As the treatment system operator, your job is important to protect human and environmental health. As you can see, it requires a great deal of operator input to achieve and maintain nitrification. Remember that factors that impact nitrification, once again, are efficiency of upstream treatment units and processes, dissolved oxygen, temperature, mean cell residence time, alkalinity, pH, CBOD removal, toxic compounds, wet weather operations, and facility design. Through effective monitoring, planning, and action, the treatment plant operator can achieve and maintain nitrification, producing an effluent that meets all permit requirements on a consistent basis, protecting our precious waterways for current and future generations to come.